Good morning. Currently, there is a great demand for 3D models of objects in the world. In particular, we are noticing the appearance of new 3D display technologies which will create the visualization and interfaces of the future and change the way we are able to assess the interpret information. With this background, we will be discussing today about ground-based 3D modeling. Before going into the details, let us discuss what is 3D modeling. So 3D modeling, or we also call it as three-dimensional modeling, is the process of developing a mathematical representation of any three-dimensional surface of an object. This object can either be inanimate object or it can be a living object also via specialized software. So basically 3D modeling problem is that for any 3D object we should have the numerous points of that object and every point of the object should be carrying x, y and z coordinates. When all these points are having x, y and z coordinate, this thing that we generate is called as a point cloud. Point cloud can be converted into a solid model also, and the product is called as a 3D model. This 3D model can be displayed as a two-dimensional image through a process called 3D rendering, or it can also be used in a computer simulation of physical phenomena. As you must have seen in the computer games and in other multimedia industry, lot of 3D simulations are being carried out. The model can also be physically created using 3D printing devices. So nowadays we are having 3D printers which can create a 3D model of the object. To create a 3D model using ground-based techniques, we have two options. The first one being the terrestrial photogrammetry, or we also call it as close-range photogrammetry, and the other one is terrestrial laser scanning. Terrestrial photogrammetry is the image-based technique, whereas terrestrial laser scanning is range-based technique. Image-based technique means we are capturing the image of the area, the images are mashed and the photogrammetric processing is carried out, and the resulting point cloud or XYZ of individual points is calculated. Terrestrial laser scanning, as we have already discussed, that it is a range-based technique. Range-based techniques means that it is an active system. The pulse is transmitted towards the object. It strikes the object and is received back. The time taken for the pulse to go up to the object and come back is noted down, and using the speed of light we find out what is the distance of the object from the particular position. So in terrestrial laser scanning, thousands and thousands of pulses are sent within a second. So similarly, so thousands and thousands of points are returned back within a second. So a very dense point cloud is generated, which can ultimately be converted into a solid 3D model. So one by one, one by one, we will start with the terrestrial photogrammetry. Okay, so terrestrial photogrammetry, or we also call it as close range photogrammetry, is a low cost alternative for 3D photorealistic modeling. Dense surface modeling using non-calibrated camera also can be carried out. The parameter estimation for generated 3D model and its reliability can be assessed. So, what is the total volume of the particular object? What is the size of the particular object? If we are modeling a tree, then all the parameters of the tree can be extracted, and these can be further utilized for some other application. we also want to make the awareness of close range photogrammetry to enable wider and wiser application across the user community. These are a few potential users who can be using close range photogrammetry. A few potential users of the technology can be administrator, decision makers, engineers, researchers in medical profession, city planners, natural resource scientists, entertainment industry, and many more. So as we have already discussed, photogrammetry can be far range photogrammetry and close range photogrammetry. Far range photogrammetry means when the camera object camera distance is more than 100 meter. Then we call it as far range photogrammetry, whereas close range photogrammetry is when the camera object distance is less. Far range photogrammetry generally is aerial and satellite photogrammetry, and close range photogrammetry is terrestrial photogrammetry when the camera is there on the ground. So when the camera is from the when we are looking from the top, the view direction is negative z direction, whereas when the camera is on the ground, the view direction is y direction. So some changes in the processing techniques have to be carried out, and then all the algorithms which we develop for aerial and satellite photogrammetry can be used for close range photogrammetry also. What are the advantages of terrestrial photogrammetry? First of all, we are able to get instantaneous image acquisition can be carried out. The cost of image acquisition is very less. The processing cost and analysis is also less. Theoretically, there is no limit to the achievable resolution. We can achieve very high resolution because resolution of the photograph depends on many factors. First of all, it depends on the camera with which you are capturing the photographs. Also, it depends on the distance between camera and object. So you can change the distance between camera and object, and so you can achieve a very high resolution image. A very high resolution image means that you can have very fine point details as well as very finer details can be visible in your 3D model. The terrestrial photogrammetry has capability of dense surface modeling, and it widens the scope of photogrammetric applications. To demonstrate how close range photogrammetry can be useful, I will be telling you about certain case studies that were carried out here at IIRS. Terrestrial photogrammetric applications, reconstruction of urban features. So what we did, we started with a very simple building, a gymnasium building here in IIRS ISRO campus. So you can see using the multiple photographs of the same object from all the directions, we were able to generate a solid model. And on this model, because this model is true to the ground, that is why it has the same coordinate system as the ground coordinate system. So whatever measurements you are making on this model would be as if you are making the same measurements on the ground. A slightly complex building. The building was captured from all the different locations. A wireframe model was generated, a solid model was generated, and it was textured also. The textured realistic model was displayed on a geoportal, ISRO's geoportal Bhuvan. So we have tried to find out whether this terrestrial photogrammetry gives us good accuracy or not. So we tried to estimate the volume of the building based on and use different type of cameras, because for terrestrial photogrammetry you can have a wide range of cameras. Even normal cameras that we use for our day-to-day application also can be used. So starting with a very simple Nokia mobile phone camera, Nokia 114 mobile phone camera, which was having a very poor resolution, 0.3 megapixel, up to Samsung Galaxy Note 2, which was the camera was having a resolution of 11 megapixel. So all these mobile phones were used to All these mobile phones were used to capture the building photographs from different distances, and the volume of the building was estimated. It was observed that up to 5 megapixel, the 5 megapixel camera, the mobile phone camera, 5 megapixel camera gives us sufficient accuracy for most of the applications. As you go on increasing the resolution of the camera, the accuracy goes on increasing, but it is up to a certain level. Also, there is a method of calibrating your camera. Calibration of the camera means that you are finding out the intrinsic parameters of the camera. So once we have done that, what is the exact focal length of the camera, what are the distortion parameters of the camera. So once we have done that, the accuracy goes on increasing. We have tried to model, to use the same approach for reconstruction of heritage assets. This is Clock Tower in Dehradun. The A building is Clock Tower of Dehradun. B is Gillespie's Monument, also in Dehradun. These two were simple structures. As you can see here, the photographs were taken from all around the object. So these are the camera stations. These are the photograph is taken from all around the object. That is why terrestrial photogrammetry is also called as multi-station convergent photogrammetry. So that from the multiple stations, multiple positions, we are capturing the photograph, and in such a way so that all the camera optical axis converge at the object. This is a FRI building also in Dehradun, which is quite a huge building, a very big structure. We were able to model it properly with terrestrial photographs. Buddha temple in Dehradun. In Buddha temple also, what we have seen is that it was observed that there is a small shift in the wire mesh model and the textured model. This error of the model was studied in detail for Buddha temple model. At 20 locations, the coordinates of wire mesh and texture model were compared. An average error of 2.5 centimeter was observed. The error increases with the complexity of the model. The structure accuracy of the model was also assessed. The model measurements were compared with DGPS survey measurement. A mean error of 2.9 centimeter was observed in the model coordinates. So this means that the model that we are able to generate using terrestrial photogrammetry is very accurate within, it is giving us accuracy in centimeters, so it can be used for any type of application. To extend the technique to the natural features, we have also tried to model the trees, the individual trees, and then tried to find out the parameters about these biophysical parameters of the tree. So a simple structured tree, a complex structured tree, a bush, other types of trees, teak tree, eucalyptus tree, all these were modeled using calibrated and uncalibrated camera, using mobile phone cameras also. And we have achieved quite satisfactory accuracy using this. Other earth surface features such as a very small object, a very small stone was modeled just to display that the technique can be used for any type of application. To demonstrate whether the technique can be applicable to estimate the excavation volume, we have done a study here and we have found very good results. The rock surface also was modeled, the landslide also was modeled. This all was done so as to demonstrate that the technique can be applied for any type of application. Now cost-effective virtual 3D mapping. We know that maps with road views let users explore places through multiple angles. One can explore the landmarks, view natural features, navigate on a street, and can even count the houses, shops, trees on the roadside. to explore the possibility of generating a roadside view which can be taken as an input for 3D GIS. An integrated approach utilizing high-resolution satellite image and terrestrial photogrammetry was applied. Mobile phone camera was utilized for terrestrial photography. As mobile phones are constantly carried, camera phones allow for capturing moments at any time which could further be processed to provide an output of reasonable accuracy. So an open source application, Thrivim, was developed. So this Thrivim is an open source freeware application for 3D street view generation. The input that is required for Thrivim are photographs, location of camera, user-defined database, and the building footprint. The output which is generated is georeference 3D model with the database. This is a process flow of Thrivim. Thrivim starts with opening a project or creating a new project or loading an existing project. We have to perform the camera calibration, point cloud generation, image segmentation, height extraction, 3D model generation, and database query can be carried out. So this is an example of point cloud which was generated using Thrivim, point cloud of Safdarjung tomb. I would like to tell you that this point cloud was generated using mobile photographs from mobile phone cameras and the open source freeware application which is Thrivim. Such type of models, 3D models, can be generated using Thrivim. These 3D models have a capability of storing shop wise or building wise or house wise database. So this type of 3D database is very useful. It can be directly put into 3D GIS and can be used for any kind of decision making. So this all was possible with the help of terrestrial photogrammetry. This is a part of 3D model in Dehradun, such type of 3D models can be displayed on geoportals. This is displayed on Bhuvan geoportal, which is ISRO's geoportal. The second type of technique used for ground-based 3D modeling was terrestrial laser scanning. As we have already discussed, it is based on the principle of LIDAR. It is light interference detection and ranging. Laser emitted from the scanner hits the object and is reflected back. The time of flight is calculated and XYZ coordinates are calculated using the time of flight. It is a non-contact surveying method of gathering thousands of points in a few minutes. So you can see here the instrument sends the thousands of beams. These beams are returned back, are reflected from the object, returns back to the instrument, and the time of flight is noted down. And like this, it goes on scanning the entire area, entire object, and we are able to generate a very dense point cloud. Entire region inside user definable window is scanned in minutes, and the accuracy that is achieved is in millimeters and centimeters. So this is a point cloud which was generated using terrestrial laser scanning. Just to emphasize that how detailed information is available in this point cloud, I have magnified a small area, and you can see the inside stairs which were going up, as well as the window panels, what was written on the window panels, the flower pots, everything, all the details have been captured in this model. This is again another building in IIRS campus, zoomed version here. You can see what all details are visible. The window panes, whether they are open, whether they are closed, this one is open, this is closed. So all these details are available. So it gives you a very detailed view of the area. We can also for realistic view, we can also color this point cloud using RGB values from the photographs that are captured. So a very realistic view of the area can be generated. An individual tree. So all the parameters about the tree, what is the height of the tree, what is the girth of the crown, what is the girth of the stem. So everything, all these parameters can be taken out and they can be put into any kind of modeling equation. We have tried to use it for cultural heritage documentation also. So this was Buddha temple and Buddha statue in Dehradun itself. So you can see we have tried to scan it using terrestrial laser scanner. A very detailed view is obtained through terrestrial laser scanner. The details of iron railing also are seen here. The carving details, everything is coming out so nicely with terrestrial laser scanning. To compare between close range photogrammetry and TLS models, for ease of acquisition, close range photogrammetry is relatively simple and quick, whereas TLS is time consuming and depends on scanning resolution. The volume of data for close range photogrammetry is less, whereas for TLS it is quite high. The quality of model is good and depends on the quality of the image. For TLS, the quality of model is very good and all the details are acquired. The measurements are slightly less accurate in case of close range photogrammetry, and also it depends upon the quality of images, whereas for TLS it is very high quality accuracy measurements can be done. So here I am showing you the models generated by close range photogrammetry and models generated by terrestrial laser scanner. The range based, we can conclude that range based point cloud, that is TLS, is dense, hence minor details are also visible. Whereas the image based technique, that is close range photogrammetry, provides good quality RGB information and it's better to visualize textures. Also geometric precision is high. So thank you so much.